When you watch an AI-generated clip of a glacier calving or a bird taking flight, you are looking at something dynamic and spatially complex. But translating a simple text prompt into moving reality requires a completely different mathematical approach than writing a paragraph of text. Large language models generate text using an autoregressive architecture. They calculate and output data strictly sequentially, predicting one single token at a time based on what came before it. If you try to build a video that way, rendering data sequentially pixel by pixel, the computation stalls out. Because of that limitation, modern visual models completely discard token prediction. Instead, they rely on a mechanism called diffusion. A diffusion model starts with a completely meaningless canvas of random noise and works backward, iteratively refining that chaos until a coherent structure emerges. To cross the chasm from natural language processing to moving pixels, engineers had to abandon sequential generation entirely. They swapped predicting the next word for predicting the removal of noise. The scale of the data is the first immediate hurdle. A single standard high-definition image is millions of pixels. If you want a video that runs 24 frames per second and is just 8 seconds long, this 2D matrix instantly extrudes into a massive 3D CLED, containing roughly 176 million individual pixels. This grid exposes the first critical engineering bottleneck: temporal consistency. The network has to somehow force physical coherence and structural alignment across every single layer of this massive grid simultaneously. If it fails, objects warp, disappear, and violate basic physics. The second bottleneck is the sheer computational load. Running deep machine learning operations across hundreds of millions of distinct data points for every single frame requires an impossible amount of processing power. A functional video generation model requires a structural solution to both problems at once. The architecture must solve the physics problem of visual coherence across time, while simultaneously solving the mathematical problem of infinite compute. The foundation of this architecture begins with single images. To teach a network how to build reality out of noise, you first have to teach it exactly how reality degrades into noise. Look closely at this cropped grid of image pixels. We apply a process called forward diffusion by introducing Gaussian noise. This means we take the precise numerical values defining the color and brightness of each individual pixel and give them a tiny randomized numerical nudge. The term Gaussian simply dictates how that randomness is applied. It maps to a normal distribution curve, establishing strict statistical boundaries for how aggressively those pixel values are allowed to fluctuate. This process operates in a rigid, iterative loop. The network takes that slightly scrambled pixel grid, steps forward in time, and injects another precise calculation of Gaussian noise. Then it steps forward and does it again. Eventually, the original data structure is completely overwritten. The image is systematically scrubbed away until the matrix contains nothing but mathematically defined randomness. The neural network is not actually learning how to generate anything during this forward process. This loop is strictly a mechanism for dataset creation. Forward diffusion generates a precise step-by-step mathematical map of how coherent visual data decays into chaos. That exact sequence of decay is what the machine learning model will be trained to reverse. Reverse diffusion is the machine learning loop where the actual generation happens. The goal is to take a corrupted matrix and incrementally subtract the noise until a clear image appears. To train the model, we feed it a completely noisy pixel matrix. Crucially, we also tell the model exactly which time step from the forward diffusion process this noisy matrix belongs to. This diagram shows the network's singular objective. It analyzes the input and outputs a predicted noise matrix. It guesses the exact numerical configuration of the static added during the preceding forward time step. We optimize the model by calculating the mathematical distance between predicted noise and actual ground truth noise. By mathematically subtracting that predicted static from the input, the matrix becomes clearer. The network executes millions of iterations of this subtraction loop across massive datasets. Over time, it learns the underlying patterns required to carve coherent physical structures out of total mathematical randomness. At this stage, the reverse diffusion loop works, but it lacks direction. If we stop here, the network will successfully pull a clear image out of the noise, but it will be entirely random. To guide the output, we inject natural language into the training process. Text prompts describing the image are vectorized into mathematical embeddings, which are passed into the network directly alongside the noisy matrix. The model analyzes these combined inputs and learns to correlate specific word vectors with highly specific patterns of noise reduction. The vector for bird trains the model to carve out a very different set of pixels than the vector for top hat. Text conditioning acts as the steering wheel. It forces the architecture away from random pixel generation and turns it into a highly directed visual synthesizer. We now have a system that can generate a 2D image from a text prompt, but a video introduces a third dimension. Computationally, a video is a 3D matrix composed of an x-axis, a y-axis, and time. The naive engineering approach is to simply force our standard 2D image diffusion model to process a batch of frames simultaneously, hoping they string together. Watch this generated clip of a coffee cup moving across a table. This is what happens when you apply a naive 2D approach to 3D video data. You get extreme flickering, physics violations, and a total lack of object permanence. The architecture fails here because it processes every single frame in isolation. The mathematical relationship between a pixel in frame 1 and that same pixel in frame 24 goes entirely uncalculated. Without a dedicated structural mechanism to map physical objects from one frame to the next, a matrix of generated images will always remain a chaotic slideshow, not a temporally coherent video. To solve the temporal bottleneck, look at how the data is restructured. The massive video matrix is sliced into a highly organized grid of smaller, overlapping 3D cubes called spatiotemporal patches. By chunking data into 3D blocks spanning multiple frames, we create a mathematical scaffold. It groups pixels across space and time so movement can be tracked. To process these patches, standard neural networks are replaced entirely by a vision transformer architecture. Transformers use an attention mechanism. As the network analyzes a sequence, the attention mechanism forces it to explicitly calculate the relevance and relationship of every individual spatiotemporal patch against all the other patches in the matrix. This solves object permanence. If an object is established at specific coordinates in frame 1, the attention mechanism directly correlates that data to its mathematically interpolated position in frame 160. Vision transformers provide the framework for temporal coherence. While models still occasionally struggle with physical accuracy, this attention mechanism allows the network to logically link the sequence of patches across the timeline, but the vision transformer slams directly into the second bottleneck. Running an attention mechanism across 176 million raw pixels is mathematically unscalable. This diagram shows the required architectural fix: data compression using an autoencoder network. The top half of this network is the encoder. It takes the massive raw pixel matrix and crushes it down into a highly dense lower dimensional representation known as latent space. This enables a crucial optimization. The entire heavy computational load of the reverse diffusion loop, predicting the noise, running the attention mechanism, subtracting the static, is executed exclusively within this tiny latent space. The model bypasses full-size pixels entirely. Once the latent matrix is completely denoised, we reach the decoder's function. It takes that cleaned, highly compressed data block and expands it back out into full-resolution image pixels. Operating in a compressed latent space solves the math problem. It reduces the processing load by orders of magnitude, making state-of-the-art video generation computationally tractable without sacrificing final resolution. We can now trace a prompt through the fully optimized inference pipeline. The initialization sequence begins here. The system generates a block of pure random noise, strictly bounded by the compressed dimensions of the autoencoder's latent space, which is then combined with the text embedding from your prompt. That tiny, noisy, latent block is immediately sliced into spatial temporal patches and passed into the vision transformer. The vision transformer executes multiple forward passes. On every single loop, it iteratively predicts and subtracts the noise, while the attention mechanism forces temporal coherence across every spatial patch. In the final step, these cleaned, temporally locked latent patches are routed through the decoder to reconstruct the full sequence of high-resolution image pixels. The inference pipeline is a synchronized system, where transformers handle physical logic and autoencoders handle the computational limits. The output from this pipeline is a coherent video. Because of the architectural constraints placed on the data, the final result is largely free of flickering or physical mapping errors. What registers to the human eye as a fluid, creative piece of motion is fundamentally a mathematical orchestration. Billions of distinct numbers have been organized into a rigid spatial and temporal structure. Synthesizing video from natural language involves higher complexity than scaling a 2D image generator. It requires a specific architectural focus on the relationships between space, time, and compressed data. State-of-the-art video models do not act as digital artists drawing pictures. They act as mathematical sculptures, meticulously discovering the physical reality hidden within a block of pure noise.
Thank you. Share and subscribe to Learn AI for more AI insights.